Okay, so today I'm going to discuss the 2025 Physics Nobel Prize, the lecture that Professor Brian Kennedy did. So basically, what it went over mainly boils down to the quantum tunneling theory, which is in quantum mechanics, there's a phenomenon where a wave function can propagate through a potential barrier, allowing particles to pass through barriers that classical physics deems impossible. So basically, what happens is that we know that you need a, due to Coulomb's law, we know that there's a certain amount of potential energy that alpha particles theoretically need to escape the nucleus of a of a radioactive element, okay? So, by all logics, they do not have enough kinetic energy to escape. They do not build enough potential energy to escape because once you leave, it all gets converted into kinetic energy. And once it's out of the cell, or once it's out of the nucleus, we can measure that, and we've recognized that the alpha particles are not moving fast enough. So there wasn't enough energy to begin with that provides us with enough kinetic energy to correlate with the amount of kinetic energy that the particle is escaping with. So theoretically, we know that alpha particles shouldn't, by classical physics standards, overcome the potential energy barrier required to escape the nucleus due to Coulomb's law. But what what was proposed in about the 1980s, 1983, was that the uncertainty principle allows the possibility of the alpha particles to escape the barrier. And what the uncertainty principle basically states is that, these alpha particles can exist anywhere in space inside the nucleus. So they kind of just appear, disappear, appear here, there. There's a certain region where they're more likely to be. But somehow, when they reach the the edge of the nucleus, uh, they overcome Coulomb's law and get repelled by the nucleus. Um, Basically, this contradicts the classical physics idea of energy, that energy is neither created, destroyed, only converted. Um, which would, by classical standards, would mean we would have to have negative energy to overcome that potential energy disconnect. So basically, we can think of it that the longer you wait, the more probability that you have for the alpha particle to escape the nucleus and escape that Coulomb's law. And our research has proven that half-life can be correlated to the probability increase. Um, and basically, we can map the this with the tunneling microscope. So it scans atoms, and it sees uh, areas where there are higher currents, and where those higher currents are, that means it has more energy, which means it has more of a probability of escaping the nucleus. But yeah, that's a little bit of a summary about what I learned. What did I already know? I already knew a little bit about quantum theory. They went over Schrodinger's equations, which was actually kind of cool. And it did spark a little bit of interest in me to do a little bit more research into this. It doesn't really relate to my studies because I am a aerospace major. But yeah, um, I hope I explained it a little bit.